Hi everyone, welcome to this week's video lecture. For this week's video lecture, we're going to be starting a new chapter. This is chapter 6 from the book, and the title of the chapter is Integer, Goal, and Nonlinear Programming Models. So far we've covered chapter 1 through 5, and all the earlier chapters focus on the linear programming category of mathematical programming models. Now, what these LP models that we've covered so far have in common is three characteristics. Number one, the decision variables are allowed to have fractional values. So we're okay with getting decimal numbers or fractional values as our solution. The second characteristic which is common across LP models is that there is a unique objective function, whether be it to maximize profit or to minimize costs. We always select one single objective function, and the aim of the model is try to achieve that objective function. The third characteristic, which was common across all the LP models that we've covered so far, is that all the mathematical expressions, the objective function, the constraints, everything has to be linear. So here in this particular chapter, we're going to learn about some of the extensions of linear programming models, and we'll try to relax each of these three basic LP conditions that I just listed. So the new models that we're going to learn about in this chapter, specifically integer, goal, and nonlinear programming models, here we are relaxing each of those three characteristics that I described. Number one, the decision variables are not allowed to have fractional or decimal values, and that particular characteristic relaxation can be extremely useful when you are solving the model where whole numbers are required as a solution. So for example, if you're trying to figure out how many airline seats should the airline company sell in order to hit a certain revenue mark, then in that case a whole number solution is required because you cannot sell half a seat to somebody. The same goes for hotel rooms. When you are selling hotel rooms, or when you are sort of renting out hotel rooms, it has to be one whole room at a time, and half a room doesn't really make sense. So we require our solutions to be whole numbers. The second class of models that we're going to look into for this chapter is goal programming. And goal programming is specifically interesting because it allows you to have more than one objectives in the model. So in the same model, you can be solving for multiple objectives at the same time. And then finally, for nonlinear programming models, you relax the assumption of having only linear variables and linear expressions in your model, because a lot of the times in real life relationships are not really linear. They have to be formulated in a nonlinear fashion for it to be more realistic. So nonlinear programming models help you achieve that purpose. For this video lecture specifically, we will introduce all three of these different models: integer, goal, and nonlinear programming models, and we'll go over the characteristics of each of them and understand what the differences across different types of integer models are. For the next videos, we're going to cover goal programming and nonlinear programming in more detail, but for the purpose of this particular video, we're going to focus on integer programming only. We will understand the different types of integer models that are available to us in order to apply to our specific problem at hand, and then we will go over examples to see how we can achieve that using Excel Solver. So let's start off the chapter with an introduction to each of these three types of models that we're going to be discussing in this module and in the next module. So sometimes when you're solving linear programming models, fractional values such as x is equals to 0.576 or y is equals to 102.4 may be valid for decision variables in many problems. A large number of business problems can be solved if the solutions are in decimals or in fractions. But a large number of business problems also can only be solved if the variables have integer values. So for example, when an airline decides how many flights to operate on a given sector, it can't decide to operate 5.2 flights. It must operate either 5 flights or 6 flights. So integer programming is an extension of an LP model that solves problems which require integer or whole number solutions. So there are different types of integer programming models, and we'll get into the details as we progress along in the chapter. But remember that this is the main difference between a regular linear programming problem and an integer linear programming problem, that you specifically ask for whole number and integer solutions because that's sort of a business requirement for that particular model. Moving on to goal programming models. Now, goal programming models are useful because sometimes the decision maker or the business manager doesn't only have one objective. Maximizing profit or minimizing cost isn't the only objective that a business has. The management may need to maximize cost, but at the same time, it also wants to maybe maximize market share. It also wants to maximize machine utilization. It also wants to maintain the employment levels that it currently has, or it also would want to minimize the effects on the environment of their business operations. So all these objectives can sometimes conflict with each other. So for example, if you're trying to minimize cost, it would be a direct conflict to maintaining full employment. So with the help of goal programming, we are extending LP models in such a way that it allows us to solve for multiple objectives simultaneously in the same model. So goal programming, the formal definition is an extension of LP that permits more than one objective to be stated. So you could have 2 or 3 objective functions in the same model trying to achieve all 3 goals at the same time simultaneously. The third type of model that we're going to be covering for chapter 6 is nonlinear programming models. Now, linear programming can, of course, be applied only to cases where the objective function and all constraints are linear. However, in real life, the relationships between different variables are not always linear. So allowing for the possibility to have nonlinear relationships between variables and having nonlinear expressions as a part of your mathematical model, nonlinear programming helps you achieve that objective, even though the variables and the different functions used in the model have nonlinear terms in them. The overall setup remains the same, but we do allow to relax the assumption of having only linear terms as a part of your models. Now that we have introduced all 3 types of models, which we're going to be covering in this chapter, let's do a deep dive into integer models. Like I said earlier, for the purpose of this video, we're only going to focus on integer models, and that too general integer variable models. So let me explain what the different types of integer models that are listed in front of you mean. So there are different types of integer models that you can have. The first one is the general integer variable model. In a general integer variable model, the variables can take any non-negative integer value or whole number value. So there are no additional restrictions here, which is why you see the term general here, because it's the most general form of integer models, and you are okay with the solution having any value as long as it's a whole number and as long as it's non-negative. If you want to be more specific about the values your variables can take, we move on to the next type of model, which is binary variable models. Just like the name suggests here, you're restricting your variables to take only two values, either 0 or 1. So your solution will always be 0, 1 values and no other value. And this is specifically useful for cases when you need a yes, no answer. So for example, if you revise or recall in chapter 5, when we were covering the shortest path model, there are decision variables were taking binary values, because you had to decide which route to take in order to get from your origin node to your destination node. So a 1 means a yes and a 0 means a no. So those types of variables are specifically useful for models where a 0, 1 is required or a yes, no type solution is required. The third type of model that we're going to discuss in detail is called pure IP problems. These are problems in which all decision variables must have integer solutions. So all the decision variables in your model are integers. On the other hand, mixed IP problems are problems where not all of your decision variables must have integer solutions. So you could have two types of decision variables, one having integer solutions and one being allowed to have fractional optimal values. We're going to discuss some examples for each of these models here as we move along. But remember that these types are not mutually exclusive from one another. So for example, you can have a pure IP problem, which is also a general integer variable problem, and you can have a mixed IP problem where some of your variables are binary variables, some of them are general integer variables, and some of them can take fractional values as well. Later on, when we move on to the next module, we'll talk about goal programming models as well, where you're going to solve for multiple objectives in the same model. Following that, we're going to be solving nonlinear models. An example of a nonlinear model objective function is given here, where the objective is to maximize profits, and the objective function is given by this mathematical expression here. And what you'll notice here is that you have a term x squared, which obviously is nonlinear, it's quadratic, and you also have another term y squared again, which is a quadratic term, so it's nonlinear. Before this, we have only solved for linear models where such terms are not allowed to be a part of the model, but now we're going to look into the possibility of allowing these terms and solving for them, for the sole reason of making your models more accurate and more realistic. And this is true for constraints as well. Okay, so now let's talk about integer models in detail. The first question that comes to mind when I define a integer model is that why can't I just use a regular LP model and then round up or round down the optimal solution that I get? Obviously, that is one possible way of handling this situation. So for example, if I solve the airline problem and my optimal solution is 5.38, then I can simply round it up to 6 flights and have 6 flights be my optimal solution. sometimes that type of generalization or that type of simplification works, but sometimes that may not be the best option at that point, and that may not even be feasible at that point. So if you look at the model formulation for an LP model and an IP model, the overall model formulation between the two, there is no real difference in the basic procedures in formulating either of those models. The only difference between an LP and an IP model is this additional requirement in an IP model that one or more of the decision variables can take on only integer values in the optimal solution. So the actual value of this integer variable, however, is limited only by the constraints in the model. So for example, values such as 0, 1, 2, 3, and so on are perfectly valid for these variables as long as these values satisfy all the constraints that have been included in your model. So in that case, if you look at an LP model and an IP model, why it would make sense to formulate your problem as an IP instead of an LP is because IP models would give you the exact solution that you require, and they would also make sure that you have enough resources to be able to get to that optimal solution because of the way the constraints are designed. If you're simply rounding up or rounding down the solutions from an LP model to use for an IP framework, then there might be a case where you might not have enough resources to do that rounding up or rounding down as required. One thing that you should keep in mind is that the IP objective function value is usually worse than the LP value. Now, what that statement means is that if you, let's say, for example, you're solving a minimum cost problem where the objective function is to minimize the total cost, and let's say the optimal solution that the LP model gives you is that the minimum cost you can achieve is $4,000 with the given amount of resources available. Now, if you solve the same model as an IP model now instead of an LP model, the objective function value that you will get will be at best equal to that LP value, or it could be worse than that LP value. So for a minimum cost problem, a worse solution would be having a total cost value which is above that 400 value that LP gave us. So for an IP minimization cost problem, you might get a solution which is a higher cost value than what an LP would give you, but it's still acceptable because it satisfies all of your constraints, and it makes sure that the solution is usable because the values are all integers. The IP solutions, if you recall from chapter 2, when we covered the graphical analysis method to solve LP problems, we made a statement at that point that all of the LP optimal values are at the corners of your feasible region. That may not always be true for an IP solution. So if you are forcing an IP restriction, that means all of your decision variables have to be whole numbers, it may not be possible at the corner points. It could also be a point inside of the feasible region, which is not a corner of the feasible region. So that's something that you should probably keep in mind as a difference between an LP model and IP model. So just to summarize, the basic framework remains the same. The only difference is that the IP model is more restrictive than the LP model because the IP model only allows the solution to have whole number values. Okay, now let's take a look at an example, for a simple example, just to demonstrate how we would formulate a model as an IP problem. This is taken directly from the book. The example that we're covering is called Harrison Electric Company. And I'll just give you a little bit of background if you don't have the chapter in front of you. Harrison Electric Company is located in Chicago, and it produces two expensive products that are popular with renovators of old historic homes. Their first product is ornate lamps, and their second product is old-fashioned ceiling fans. Now, both the lamps and ceiling fans require a two-step production process, which involves wiring and assembly time. It takes about 2 hours to wire each lamp and 3 hours to wire a ceiling fan. And in total, they have about 12 hours of wiring available. For assembly, it takes 6 hours to assemble a lamp, whereas it takes 5 hours to assemble a fan, and in total, they have 30 hours of availability for assembly specifically. Now, the profit contributions for each of these products are also given in the table, 600 and 700. If we move on to formulating the model, this is a simple model that we've covered multiple times. An example for this, an example like this. So we define our decision variables. We define them as L for lamps and F for fans. And the exact definition is that L refers to the number of lamps that this company can produce, and F refers to the number of ceiling fans that the company should produce given the amount of resources available. Now, what you'll notice here is that we are imposing one small addition here in the definition of decision variables, that L and F can only be integer values, which means that they can only be whole numbers. If you get a solution like 3.5 lamps, that's unacceptable, because what does a 0.5 lamp mean? How can you sell half a lamp? Nobody's going to buy a half a lamp. And what does that even mean in terms of that particular product? So we require only whole number values which are realistic and usable. So now that we've defined our decision variables as L and F, and L and F are both integers, we move on to the objective function. It's a simple maximization model where you're trying to maximize the total profit within the context of how many lamps to produce and sell and how many fans to produce and sell. So the objective function is 600L plus 700F, subject to the three usual constraints that we generally have in a product mix problem like this. The first constraint is for the wiring hours, and the second constraint is for the availability of assembly hours, and finally the non-negativity constraints. So if you look at this model formulation, it looks exactly the same as we would have done in an LP model. There doesn't seem to be any differences between the formulation of this and an LP model. The only notable difference is in the definition of decision variables, where we said that they can only be integer values. Everything else is the same as what we've been covering in all the earlier chapters. Okay, let's take a look at the graphical solution for this simple model that we just formulated for Harrison Electric Company. Now, this is a little revision from chapter 2, where we covered how we can get an optimal solution using the graphical approach. Remember that the graphical approach is usable for models with only 2 decision variables. If your model has more than 2 decision variables, you can't solve this graphical solution. But because our example model is relatively simple and we only have 2 variables, L and F, we can try to demonstrate the differences between an LP model and an IP model from a graphical point of view. So here we've chosen to put F on the y-axis and L on the x-axis. And if you remember from chapter 2, the way we get the graphical solution is we start with the constraints first. So we draw the lines for each of the constraints on our graph and then identify the feasible region. The corner points of your feasible region would be potential optimal values for your solution. So here, since we had two constraint equations other than the non-negativity constraints, so we have drawn the lines for each of those two constraints. The first line is here for the wiring, and then second you have for the assembly. So given that you have 30 hours of assembly available and 12 hours of wiring, and you only need to use less than these available hours, the feasible region is going to be the region below each of these lines, and the common region is coded here in brown color. So this brown shaded area is where you will find your optimal solution. So this is your feasible region. Now, if you solve for the optimal solution, the optimal solution can either be this corner point here, this corner point here, or this corner point here. So you have three potentials for the optimal solution, and just by I'm not going to solve it right now, but just by solving it, you find out that this particular corner point is the optimal value for your solution. However, there's a simple issue here, that the values that you get for the optimal solution tells you to produce and sell 3.75 lamps and 1.5 fans. Now, again, like we said, that's not an accurate depiction of what we can produce and sell because they're not whole numbers. So the next obvious choice would be to round up these values, right? You round up L to 4 and you round up F to 2. Now let's take a look at where it is on the graph. If I round up L to 4 and F to 2, it's referring to this point over here. And if it's obvious now that that particular point is outside of our feasible region, which means that if I produce 4 lamps and 2 fans, I need to have more resources than what the values were given in my constraints. So this potential solution is actually not feasible, so it's not a solution anymore. So just simply rounding up your LP solution is not acceptable in this case. And the next feasible region, so obviously you can be the devil's advocate and be like, why do I have to solve an IP model when I can simply round it down then? So you round down the value for F to 1 and L to 4. Now, if you do that, what happens next is that you can calculate how much your profit will be if you round down your F optimal value and you round up your L optimal value. So by trying out L is equals to 4 and F is equals to 1, and you put it in the objective function, you get a profit of 3,100, whereas in the LP model you were getting a profit of 3,300. This is what I meant by the fact that an IP solution will always be worse than an LP solution. Here you're getting a profit of 3,300, and here you're getting a profit value which is less than that 3,300. So however, when you consider this situation here, what happened is that when you were solving an LP problem, it was giving you an optimal value that was not usable. So in order to make it usable, you convert the model into an IP model and solve it as an IP model so that you can achieve a profit value which is acceptable, and it is also feasible given the constraints that you have in the model. So now that we've established a case for solving the problem as an IP problem instead of an LP problem, let's move on to Excel and look at what the solution suggests. I have created a template where I've added all of the input variables and their values in this Excel sheet over here. The only things that I need to add is the formulas for profit and each of these left-hand side for constraints. So I'll add the profit formula in here, which is a sum product of our decision variables along with the profit contributions. And the left-hand side for the first constraint is the sum product of the decision variables with the coefficients. And finally, the last constraint, again, sum product of our decision variables with the coefficients, with the respective coefficients. So now that I've added all the formulas necessary for solving this, I can move on to the solver now. So I've added my objective, which is in cell D6, to my solver window. I'm maximizing this subject to my changing variables, the yellow cells, and the constraints that I've added as a part of the model. The only change in this solver window here is this additional constraint to set your decision variable values only to integer. So I'll just delete this and add this constraint in front of you so that you can learn how to add an integer constraint in your model. So here what I'll do is click on add, and when this window pops up, I want my decision variables, which are these cells in yellow, to be integers. So I'll click on this little down arrow that I see in the middle, and instead of selecting the less than, equal, or greater than signs, I'll select int, which stands for integer. So whenever you select that, the right hand side automatically is populated as integer, and you press OK, and that's how you would get the decision variables to be integers. And now we're ready to solve for it. And when you do, you get an optimal solution that are whole numbers. So you should be producing 3 lamps and 2 fans. Now, if I go back to my graphical solution, this is not what I had in mind when I was looking at the graphical solution, because when I was looking at the graphical solution, using the LP model, I was trying to make 4 lamps and 1 fan, and the profit was 3,100. Whereas when I solved it as an IP model, it's giving me a higher profit. It's still lower than the profit for the LP model, but it's better than just rounding up the solution for the LP model. So this way, it helps you understand that formulating a model as an IP model can sometimes be extremely useful, rather than just rounding up or rounding down the solutions of an LP model.